Hi and welcome back to another video. So, I was browsing YouTube myself and came across this example here. We have a wedge and a block on top of it. There is no friction between the ground and wedge and also between the wedge and the box. In his video, the creator Faculty of Khan shows how to formulate the system equations for this sliding block example and then solves them analytically to figure out when the box hits the bottom of the ramp. As the box slides down, it pushes the wedge back, leading to a change of acceleration in the block and so on. I figured this would make for an interesting video where we use numerical simulation instead, and then we can analyze two things. First, how to reformulate the connected system equations of this example, and second, we can compare our numerical simulation results with the exact solution of the problem to see how big the error of the numerical simulation actually is. We start with the system, how it moves and where the coordinates are. Then we continue with the equations of motion and how to formulate the equations required in the numerical simulator. Afterwards we go over the implemented code and finally take a look at some animations to see how we can validate our results. We take this wedge here and put a mass on top and make some assumptions. First, we assume that the wedge can freely slide from side to side. There is some influence from this box, obviously. Speaking of, the box can slide up and down on the wedge. Gravity acts downwards. So given we start with wedge velocity equal to 0, the box will slide downwards. For simplicity, we assume no friction between any of the surfaces. If we now put the box on top of the wedge and release it, it will slide down, push the wedge back in the process, and arrive at the bottom after some time. Depending how heavy both elements are, this will take shorter or longer. Since the box is bound to the wedge and it cannot lift off, you can use the two variables highlighted on screen to describe the position. If you are interested in the absolute x and y position of the box, you can calculate it with the help of Q1 and Q2 and the angle of the wedge. I will go into a bit more detail why something like this is beneficial in the video where I cover Lagrange's principle. With those variables describing the motion of our elements, the equations of motion come out to look like this, and you might already see an issue. Unlike the equations in the previous videos, where the accelerations in all directions were decoupled straight away, here we have both accelerations in both equations. We need to sort that out first and get our equations to a form in which we can implement them in simulation. This is something you might run into frequently if you look at systems with more interacting elements. One way to solve this is to first write everything down in matrix form. This way our first equation is here, and our second equation can be found here. Then we can multiply both sides with the inverse of this matrix. The only step left for us afterwards is to rewrite the system to only require a single integration like this. Here Q1 2 dot and Q2 2 dot are calculated by solving the equation up here, and Q1 dot and Q2 dot adjust the states in the simulation directly. You will see this in the implemented code as well. Speaking of the code, I put it on GitHub again. The link is in the description in case you want to play around with it. It consists of the main function, where we first set up everything we need for our plots, define the parameters used in simulation. Then we define our event handling, the start values for our simulation, and call the simulator itself. As mentioned at the start, there exists an analytical solution to this problem, and we calculate this down here. Afterwards, we can compare it with our simulation results. At the end, we plot the results. The event handling is almost identical to the one from last month's video. Our event to detect is when the box hits the endpoint at length L. Here we set the simulation to stop when this happens, and lastly set our direction to not matter. The last code part is the function where we describe the dynamic movement. after the documentation of the function, we split the state vector into its individual components and use that to calculate our change of state. Solving the matrix this way is quicker in Matlab than calculating the inverse. It will not matter for this 2x2 system like we have here, but in a bigger system with more states it can make a difference. In the last step we return our complete change of state vector. I know I speedrun the code this time, but I covered those exact steps in more detail and with more insight in the previous 2 videos. If you need the information why certain steps are done this way, best go check those out as well. If this is the first video you see from my channel, I did not have the microphone I have right now back then. The other videos are linked in the description, just keep that with the microphone in mind. Let's check out the results of the simulation. In this first one, the mass of the wedge is 10 times higher than the mass of the box sliding down. As the box slides down, it pushes the wedge back a little bit, as you can see. Let's move the mass back up a bit and put the markings back in for reference before bringing up the static plots. First, the position of the mass Q1 relative to the position of the wedge. Here we have the position from our numerical simulation, and here the result for our analytical solution. The point in time detected by the numerical simulation when we hit the bottom of the wedge is pretty much identical to the time calculated analytically as well. Because the results are so similar, it makes way more sense to look at the difference between the 2 signals. The mass slides down by 1 meter, and the difference between the numerical simulation and the exact analytical solution is only around 2 times 10 to the power of minus 15. And yes, we are comparing a simulation to a different numerical calculation, and not a calculation to a real-world example. But I think it is fairly impressive just how accurate a numerical simulation can be. Even better, the numerical simulation only takes 8 steps to reach this point here, and the rest of those results here are just interpolated from those points. The comparison to the exact solution shows how accurate this interpolation step is as well. Good stuff. In next month's video, I will cover how this numerical integration works step by step. Lastly, over here on the right hand side, I put the movement of the wedge itself. Not that much to see, just that it moves back by around 8 mm in total. If we now increase the mass of our box to be equal to the mass of our wedge and run the animation again, let's look at it again and put them side to side this time. As we let the animation run, we see that, unsurprisingly, the increased mass of the box pushes the wedge back even further. If we bring this to the extreme and increase the mass of the box to be 100 times and 1 million times bigger than the mass of the wedge, we see the same thing. That is unsurprising, but what is kind of cool is that our simulation has no idea that the box actually wants to move straight down. It calculates the interaction between the wedge and the box, and if we push it to the extreme, we basically end up with a box falling down as if in free fall, and the wedge is just pushed out. That is what we see in this last animation here. Our box reaches the end point of the wedge after 0.319 seconds, which is exactly the time it takes to traverse this height in free fall. We can derive this time by first calculating the vertical height that needs to be traversed from the wedge length and angle, then calculate the distance our box travels if accelerating with the gravitational acceleration over time t. With the numerical parameters and the solved equation, the time comes out to be 0.319 seconds. And you can see that this is the exact same time returned by our simulation. That was about everything for now, bit of a quicker one this month. In the video next month, we will cover how the ODE45 integrator works and take a deep dive into the numerical wizardry going on. If you found this video interesting or you were surprised by how accurate the simulation can be, hit that like button. It really helps the channel, so thanks. Make sure to subscribe and stay tuned for the next videos to come. Make sure to check out Faculty of Khan's video on the sliding box, where he calculates the analytical solution as well. Thank you very much for watching. Bye for now.